Okay, this is the third part, chapter 3C. I have already released 2 CDs. That part is 3A, that's 3B, and this is 3C will be released today. We'll be looking at minimum or maximum phase, all pass filters, second order resonators, stability of the filter, notch filter, and especially digital oscillators. What is a digital oscillator and how do you design a digital oscillator? We'll look at that. Before I start, I just want to do one example based on the last lecture. Here is an example. Take an application where a constant group delay filters are used. Constant group delay means you want to make sure that all the signals, when they're filtered, they all arrive at the output at the same time. So the only filters that can give constant group delay is FIR, linear phase filters, and we do need constant group delay for when you are filtering music signals or video signals. Music signals actually depends on the harmonics, and if the harmonics arrive at the output of the filter at a different time, when you combine them together, you'll get distortion. So you want to make sure if it's a music signal or video signal, they are filtered using FIR filter with a linear phase. Whereas speech signals, they can be filtered with any filters because phase, the ear is not sensitive for phase distortion. So you want to make sure constant group delay filters are used for these two. Here is another example where you have to draw a parallel and a cascade realization for the transfer function given here. This is already in cascade. Therefore, all you need to do is to implement that and implement that. So we have got a gain of 2, and then we do basically a first order feedback filter. So here's the feedback, that's 0.5, that's the first order, in cascade with another order. So basically that's what you do in this case. Now, for that cascade realization, for parallel realization, you get the transfer function, put them in a partial fraction form. So that's your transfer function, become as a constant A and constant B, and add them together. And you know how to calculate a partial when you put them in a partial fraction, the values, this is A, this is B. And if you actually do it, A becomes 4 and B becomes -2. Once you have it, you implement this filter, you implement that one and add them together. Well, you can implement plus here and put a minus here, then you can add them together. So implementation of this is basically, there you are, and multiply by 4 all the scale. Then the implementation of this is the feedback part, multiply by 2, but we have a minus, so multiply by -2 here, and then add them together, you get the parallel structure. These are just an example based on last time that we have done, okay? Now we look at minimum phase, maximum phase, and mixed phase system. How do we design? If you consider 2 FIR filters, and look at the filter, FIR filter, where you've got a, in this case, this will be, if you write this one, it will become as Z plus half divided by Z. So you've got a pole here, which does basically nothing, and that's a 0 with this here, because that's equal to -half. So the 0 is minus 0.5, which is inside the unit circle. This is mod that. This is mod that equal to 1. When you now take 1 over this, that means you reflect the pole outside there, so reflect the 0, sorry, and that becomes 1 over minus 0.5, that's called reflection, and which has become 2, -2. And you see now, if you do that, your 0 is now here outside the unit circle. And the transfer function, if you write for that, this structure, it will be H is equal to, H dash is equal to Z underneath for that. That one will be Z plus 2. If you write this transfer function and if you reorder them, it will become this one. And quite a lot of you will be wondering, now this one and this one are not exactly same, because you multiply by 2, it will be 1 plus 2 to the minus 1 divided by. So if you simplify this, you will get that plus 2 divided by that, exactly what you have, times 2. So you might ask a question, why do you have this 2? Well, when you reflect on this one, you want to make sure the DC gain is almost same, or the gain is, you don't want to change the gain. So you will normally, what's the DC gain? That means this is equal to 1, is that right? So 1 plus half, this is equal to 1, 1 plus half, that gives you the same DC gain. So you need to make sure the pole zero patterns are right, reflected, but there's a gain factor has to be put in if you want to have the same gain. But having said all of those, if you now go and do the transfer function for this, get the magnitude response, h1 theta, which you know how to do it, and then find out mod h2 theta, and you can find, you will show these two have same magnitude response. So by reflecting the 0 outside or reflecting the 0 inside, doesn't matter, whichever, reflecting in inverse 1 over the 0 value, you can actually make, and you can show that the magnitude response are same. But if you look at the phase response of them, they're different. So the zeros actually shift the magnitude, but by moving the 0 inside the unit circle or outside the unit circle by this inverse property, you will get same magnitude response but different phase. From that, I'm going to define what's minimum phase, maximum phase. So let's go with this, and h1 theta is this one, h2 theta is this one, and you can show h1 theta plus h1 theta is equal to h2 theta is equal to that. So the magnitude characteristics of two filters are identical because the roots are reciprocal. That means reflecting. If one of the roots is equal to rho, and the second one is 1 over rho. So if you have that, that means reciprocal. One root is reciprocal, the other. The magnitude response will be same, but the phase response are not same. If you work out the phase from here, which you know how to do it, if you all write a MATLAB code, it shows you the phase, and if you plot that, you will see here on the next line, basically for the filter 1, which is, this is phi 1, that's by the way, I think there's an error here, and this is phi 2. You will find for phase 1, for the first filter, this is your phase change. It starts from 0 and ends at 0. And for second filter, the phase change is 0 and then it's phi here at that point. So what is the phase change? You go on to the next slide and show you. What you do, you say, what's the phase 1 at pi, and what's the phase at 0, and if you subtract this, so go back to your diagram, in this case, beg your pardon, in this case, at that point, phase 1 theta, which is equal to 0, is equal to 0, this is 0, this is 1. At that point, phase 1 pi is equal to 0. So if you subtract this one from that, the difference is 0. So you will find that for minimum phase filters, this is true. It doesn't need to be 0. In some case, when you subtract this, it will have a smaller value. But I'll come back to that in a minute. And if you go and do the same thing for the second one, that's phi 2. The second phase one is like that, right? Like that, that's pi, and that's minus pi here. Sorry, that's plus pi here, and that's also pi, and that's also minus pi. Find out the phase at that point, which is 0. Find out the phase at pi, which is pi. Pi 2 pi is that's pi. So pi minus 0 is minus. So this is sorry, at that point it's minus pi here. Sorry, that's minus pi. So minus pi minus 0 is minus pi radius. So what's the net phase change? That's what we are trying to find. What is the net phase change it goes through? In this case, it goes through minus pi radians. As a consequence of these two different phase characteristics, we call the first filter is the minimum phase, and the second one is the maximum phase filter. So if a filter with the m zeros, many zeros, has some of the zeros inside the unit circle and remaining outside the unit circle, then we call mixed phase. So now we come in and say, right, here are the two cases. In the first case, what did we have? In the first filter, what did we have? Go back to the first filter. First filter we had, if you look at the 0, it was inside. For the second filter, the 0 was reflected, so it was here outside. So if the 0 is inside the unit circle, we show that the phase difference, net phase change, is basically 0 we had earlier. And in this case, when the 0 is outside, net phase change is minus pi. That's got a value. So minimum phase means we can conclude that all zeros have to be inside the unit circle. For maximum phase, they have to be outside the unit circle. For mixed phase, they could have inside and outside. There are the two conditions. So you could have minimum phase filter, maximum phase filter, and mixed phase filter. So we've got an example next to show you here. In this case, look at the minimum phase property of FIR filter. Carries over to IIR. So we have got a filter here. We know all the poles have to be inside the unit circle, so we don't worry about the poles. It's only zeros we look at it. So B set is 0. It has got real and imaginary zeros. Here is 1, 2 complex conjugate zeros, and there's another real zeros. All the zeros are inside the unit circle. Therefore, the phase change is going to be minimum. If you work out the phase at 0, phase at pi, and work out the value, it will be a smaller value here. It can be 0 as well. If you go for the next one, where the zeros are outside, and it will provide you maximum phase. And if you plot this graph, and you will see the phase change will be maximum. Phase at 0, phase at pi, calculate them, subtract them, you will see the difference. Mixed phase, you will have probably a 0 outside, some zeros inside, and then systems called mixed phase. So I have an example to demonstrate these phase differences. Have a look. For a given magnitude response, the minimum phase system, so magnitude response 6, has the smallest magnitude phase at every frequency. Yeah, it's basically what I'm trying to say is it's the smallest deviation from 0. That's what I'm after. I'm after for a minimum phase system. It's the smallest deviation from 0. Okay. So let me go through this diagram I'm looking for. Here's an example. Let's demonstrate this through the example. Okay. Here's I have a 4th order filter. It all contains zeros. So I plot the zeros, and I have got 2 zeros here, 2 zeros here. They are complex conjugate. And this distance is 0.7. What I do then is I take one of the zero outside, reflect them. So if this is tau, it comes there. one of them out. Still I will have one inside. So I've got one inside, one outside. Then I move all of them outside. So you are reflecting. Basically you are reflecting. You are getting a reciprocal. If you reflect them, what does that mean? The magnitude response has to be same. The phase change, net phase change for this is minimum. That's what it's called, minimum phase. Net phase change is going to be kind of mixed in between this and this. Net phase change is going to be maximum. So how do you do this? Let's plot the graph or magnitude and phase response. Here is the magnitude response. For all three filters, the magnitude response looks the same. That's what's the magnitude response for all three filters. Now you look at the first filter, and where all the zeros are inside the unit circle, and the phase is at that point is 0, at that point is 0, and the difference is minimum. Take the mixed phase, where one zero out, one other inside, and you work out the phase. You can see at that point 0, at pi, this is pi, it's not 0. And you take the maximum phase, these are out. So you take the maximum phase where all the zeros are outside and find out the phase at 0, phase at pi, you see, is maximum. It's the highest. The deviation for this is 0, deviation for this is that much, the deviation for the maximum phase is that much. So from the graph you can say, if you do reflect the magnitude, if you do reflect the zeros, you will find the maximum response of the system are same, but the phase response is different. Depends if the zeros are all inside the unit circle is the minimum phase. The change at that point to that point, if you subtract them, that is 0. 0 minus 0 is 0. If you take mixed phase, just take the value here and subtract it, that's got a value. Take the maximum phase, the value is higher, that minus that is large. So maximum phase will have a maximum net change. So by looking at the zeros, you can simply say whether you're going to have a mixed phase or minimum phase or maximum phase. You may ask a question of where do we use them? There are occasions where we have to design filter, no change on the magnitude. Magnitude response for the filters have to be same, but the phase you want to alter. In that case, you can use this type of filter. Okay? There's another type which is called all-pass filter, where the magnitude response is flat, and we'll come back to that in a minute. Here's an example I want you to do. A third-order FIR filter has a transfer function given by this. This is the transfer function of a third-order FIR filter. They want you to select a filter, a new filter, with a minimum phase. So you must make sure the phase is minimum. In this case, if you factorize that, you get that one, and that one, and that one. If you now divide this by 2, divide that by 3, divide that by 2, you take 2 times 3 times 12 comes out, and this is your zeros. If you plot the zeros, this will be at 1.5, this will be at 1.1 and 1/3, this will be 2.5 positions. The zeros, all of them are outside the unit circle. All these zeros are outside the unit circle. So what do you think? It's a maximum phase. Now you want to make sure this becomes a minimum phase. So what you do? Go to the next page. So here are my the zeros. There's one zero I have here. There's another one I have. Another one I have. Maximum phase. I want to make it minimum. So I reflect it. I reflect this back in. So 3 over 2 will become 2 over 3. And I reflect this back one in here. Minus 5 over 2 will become minus 2 over 5. And I reflect this one back in here. That's become minus 4 over 3 will become minus 3 over 4. Now you've got all the zeros. Now you have got all of them inside the unit circle. That become minimum phase. So my transfer function now become what? Okay? Or I go back to my transfer function. This 3 over 2 now will become 2 over 3. 4 over 3 will become 3 over 4. 5 over 2 become 2 over 5 because I want a reciprocal of them. I do that. So I do that on the next slide. That's what I did. That. Now what happened is, you can have a look here. If you go back here, that multiplied by that, look at the DC gain. Those three, DC gain means that's 1, that's 1, that's 1. Because e to the minus j theta, that's equal to e to the j theta. Theta equal to 0 means that's equal to 1. Right? That means these are 1. So find the gain on the top and the bottom, DC gain, and you will find you have 12 here. To have the same DC gain, you must select a number. How do you select a number? Well, substitute set 1 equal to minus 1. So set minus 1 equal to 1. DC gain that's equal to 1. That's equal to 1. And these are 1. Work out the gain such that this value and the value previously is this one. Whatever you get here with the 12, they should be exactly same. So in order to have that, what you need to do is you must find the value of k. So I'm going to leave that to you to find out what's the value of k. So remember, when you do the reflection, the zeros look reflected, but the gain has to be made same. You must have a constant factor, naturally, because the DC gain will go out. Or that doesn't need to be DC gain. Any gain has to be same. So easiest to check the DC gain. So you must select the value of k such that the DC gain of this filter and the DC gain of the previous filter, this one, must be same. Okay? So you must try that yourself. If you do that, the reflection now gives you minimum phase and the magnitude response, both of them will match. Okay? The next section is all-pass filters. Now, we looked at maximum phase, minimum phase, and mixed phase filters. Now, all-pass filters. A filter that passes all the frequency without attenuating. Okay. The simplest example of an all-pass filter is a pure delay system with h set equal to, no, that's not right. That's set to the minus k. I think it's right in your lecture notes, but on the. And if you go back in this chapter and the second CD, when we plotted the phase response, we have plotted a phase response for a delay system, and they were linear. If you have a look at it. Anyway, a more interesting all-pass filter is one that is described here. You will find when you look at all-pass filter, that coefficient is equal to the last coefficient there. And similarly, you will find that this coefficient is equal to that, and also that one, this A naught, should be here. You can have A naught here. They should be same. This should be A naught. So what we normally do is, this should be A naught really. We don't normally have A naught here, right? So if you keep this as 1, what you have to do is, you take out A naught from here, out of the bracket. So all these are divided by A naught, A naught, A naught. This becomes 1. So that one and that one matches. This one becomes A1 over A naught, AL over A naught. Now if you make A naught is 1, then it's fine. You don't need to take out A naught. So in that case, in this particular example, what they've done is, even though it's written, they made this one equal to 1. So that's fine. So that coefficient matches that one. The next one matches this one. Similarly, if you go from this way, that one should match the last one, the coefficient. If they are like switched around like that, between the numerator and the denominator, they give you all-pass filter. And we will show you an example in a minute. So we define a polynomial that a that as this. That these are all zeros, where a naught is 1. And then you have a polynomial which heads at, which is equal to such the minus L a such the minus 1 divided by h a sat. This means you are taking complex conjugate and you are multiplying. If you do that, you will get this one, which is h sat multiplied by h minus that, which we can show which is equal to 1. And this is an all-pass filter. Unless you look at it very carefully, you may find this is not easy for you to understand. So you go back to the example and then come back here. So let's take an example here. This is an all-pass filter. Have a look at this example. In this example, you have got a 0 here. You've got a pole here which is at A. So that's your pole. And you have to make sure the gains are 0. So then this is reflected here. The pole is reflected into 0. If you do that, it will become that's your transfer function. Now if you simplify the transfer function, what you would have is a minus s to the minus 1 divided by 1 over a, leave that the constant, 1 minus a s to the minus 1. See that? That's what you'll have here. A is less than 1. That means that a is same, that coefficient 1 and that 1 is same, not the signs, just the coefficient only. In that case, it becomes an all-pass filter. So if you want to get an all-pass filter, you must have one pole and one 0 for all-pass filter. You follow? How do you have one pole and a 1 0 such that the magnitude response is same? Well, the best thing here is, have a look here. In this case, one pole, they must be inside, pole must be inside. 1 0, you reflect the pole's position to outside and replace it by a 0. So when you do that, you will get, here's this one and that's our one. Find out the magnitude response and magnitude response of that. So you have got h sat equal to, from this equation, equal to 1 over a times a minus s to the minus 1 divided by 1 minus a s to the minus 1. Yeah, go and find out h theta for this. You will find that will become a 1. That means passes all the frequencies. Same condition here. Where is the pole? Resonant pole here. Here we've got a resonant pole. That's like at somewhere peaking like that at theta naught. And I want to make sure I want to cancel that exactly. So I could have a 0 reflected outside. If this is R, this is 1 over R at the same frequency. So I could have a 0 going like that, exactly opposite, exactly going that. When they each cancel out, when you do that, you get an all-pass filter. So that is how you get your all-pass filter. Right. So here are some examples now. We're going to look at the example. Here's the first one. How do you find the magnitude response? You take the normal response multiplied by conjugate, which is exactly the same as the transform with s to the minus 1. They're both same. Either you do this or that. When you do this one, this is h theta, this is h conjugate. So the minus sign will become plus now here. And you multiply this out, you get that one, and then that one. They both cancel, you get a squared. And if you want to get the phase response, then you multiply these out and then work out your phase. Like this is your first filter, this is your second one, and Well, it's not the second one. The phase response, all you need to do, what am I saying? What you need to do is write the transfer function for the first one and multiply by complex conjugate. And I think here there's an error. What's the error here? Minus. Yeah, you don't need to do complex conjugate. You can just do it this way as well. You just multiply by its value again here in the top. And if you combine them, you get this one is the denominator, that one is the numerator. Now you separate the real part and imaginary part. Imaginary part divided by the real part is your phase. Tan inverse of that is your phase function. And you can plot the phase, and you will find, if you plot it, for changing your value of A, for the first one, phase I am plotting. If you select A equal to 0.5, your phase response changes like that. If you select A is equal to minus 0.5, it's 0 here, and it just goes into the negative. If you select A equal to 0.8, that's your phase response. It's a nonlinear response, and phase is different. And you can see the magnitude remains same, but the phase is different because your transfer function h dash is equal to z minus 1 over A. So the other way around is 1 minus 1 over A set to the minus 1 divided by 1 minus A set to the minus 1. That's your transfer function. This is your pole. This is reflected, so that's your 0. Now, if you find the phase response by varying the value of A, you will find you can vary the value of A, the magnitude of the response remains same, but the phase changes. You see that? So that's what is being explained there. The phase changes a lot, but the magnitude response remains same. So that's why I have read it here. I've explained here. So far, we've done two sections. One is minimum phase, maximum phase, mixed phase, and then all pass filters. If you use minimum phase filters, and if you reflect zeros, any zeros which is outside the unit circle inside the unit circle, it becomes minimum phase. And if you ever reflect zeros, what's inside to the outside, outside to the inside, their magnitude response are same, but the phase response are different. Okay? If you take all pass filter, you make sure that wherever the pole position is, keep it inside the unit circle and reflect the pole position to outside and convert that into a zero. And if you do that, then it's an all pass filter with a different phase. So where do you use all pass filter? You want a signal not attenuated, but phase to be changed. Use all pass filter. We now come to second order resonant filter. We have done this before. It's a resonant filter. So basically, what is resonant? We know that we must have a complex pole at an angle theta there. This position is theta equal to 0. This position is theta equal to pi. Remember? Right. So how do you write an equation? Basically, it's a second order system. Immediately, second order system is that's a simple equation you can write for a structure you can write for a second order. If that's the case, let's write the transfer function for this. If you write the transfer function, that's the transfer function for that. We know that yn over that is equal to yn times this one. So this minus will be plus 2 pluses. That's y. And if you simplify, that is your transfer function of that system. Let's write that from the pole 0 position, this is only pole, write the transfer function for that. Which is easy because all we need to do here is that find out if this is r, this is cos theta, find out that value. That is r is the j theta, which is r cos theta naught plus jr sin theta naught. This one is re minus j theta naught, r cos theta naught minus jr sin theta naught. That's this position. Now we put in a transfer function. How do you get transfer function? You can say h dash is equal to 1 over z minus p1 multiplied by z minus p2. You can write that from there. And for P1 and P2, substitute these values. So if you go to the next slide, that's what is happening here. Here's your original one from the structure, and this is the one what I've drawn from the unit circle. Now you continue expanding that. It comes there, from there to there, and this is cos 2 cos theta naught. So that's what you get. Now you have to say, right, I had a second order structure, resonance structure. I got a second order pole superposition. I got a transfer function from here. I got a transfer function from here. I'm going to map them. I'm going to match them, both of them. How am I going to do it? I just say, right, here you go. You say, if V1 has to be equal to minus 2r cos theta naught, they are exactly the same. So V2 has to be equal to r squared. So I can now write V2 equal to r squared, V1 equal to that. So cos theta naught is equal to minus. I have done this in chapter 1 of part B, second order. So this is called the resonance frequency of the filter. Or the second order filter. The filter response, remember, theta, phi, it's all pole, so it will be like that. Resonance is as the resonance frequency theta naught. If you make r, your r there, very close to the unit circle, this will get very sharp and come down like that. So the bandwidth, the 3 dB bandwidth here is larger, here is smaller. So it's getting narrow and narrow as you move this pole here. And when it's almost near the unit circle, it will really peak up like that. And the gain is too high. So the next question is, if that's the case, I'm talking about now, here is the 0 and here is the pole, and I'm going to move this r little by little here. When it comes to unit circle, what happened? When it goes outside the unit circle, what happened? The pole, as you know, if you move them outside the unit circle, your system goes unstable. If it is on the unit circle, its margin is stable. If it's inside the unit circle, it's stable. Okay. So we must derive conditions for this. Inside, on the unit circle, outside the unit circle for a second order system. The reason we study second order system is if you have an 8th order system, you can say one second order, followed by another second order, followed by another one, and the another one. 4 second order will give you 8th order system. So when you are given an 8th order system, you don't study the 8th order system as one whole system. You study them as 4 second order system cascaded. Therefore, we spend a lot of time in understanding a second order system. Once you know, you can expand that further. So, how do we go on? Let's take this equation, and that's your second order poles, and find out its roots. Roots are using minus b plus or minus root b squared minus 4ac over 2a, and that's what you get. b1 minus b2. Now we know that we've got, these are the poles. Now we can say that once you know the poles position, that's the pole position. You know its mode value, that's the dead distance, must be less than 1, and the second also less than 1. Okay, they're conjugated. For stability, we know B2 should be less than 1. B2 is your coefficient, which is it's at 1 over 1 plus B1 to the minus 1 plus B2 to the minus 2. We just showed earlier B2 is equal to R squared. R is the radius. For stability, B2 has to be less than 1. So that's another condition we can write. And for marginally stable, B2 could be on the unit circle. So if you're on the unit circle, we can say it's going to be stable or unstable between just marginally stable. If you make any disturbance, it goes unstable. Don't think it's going to go stable. Most of the time it goes unstable. Okay? So marginally stable, you have to be careful. If you assume that the poles are complex, then we know b squared minus 4ac should be less than 0. In our case, b1 squared minus 4b2. Go back to your equation, this page, and b1 squared minus 4b2 should be less than 0. So that's less than 0. That gives you B1 is less than 4B2. That gives you B1 is less than that. We are assuming B2 is positive. If this is greater than 0 or equal to 0, then we get real roots. We can actually use this condition and draw in a B1, B2 plane. This is B1 plane, this is B2. For the equation hits that, which is equal to that squared over 1 plus B1 to the minus 1 plus B2 to the minus 2 for that equation. We draw all the conditions. When you do all the conditions, you can actually show that the whole stability can be related to a stability triangle on a B1 and a B2 plane. Now on the coefficient plane, not on the roots plane. We know on the roots what they are, on the coefficient plane. And we will show that the maximum value of B1 can be only 2 and the minimum is minus 2. And B2 can be maximum 1. And that line is the marginally stable one. B2 means R squared equal to 1. So that's the marginally stable. It can be minus 1. And we can also show from the previous equation, you can look at it, the distributive mathematics, that this line is the parabola of that equation. And if you have complex conjugate poles, they will fall in here. If they are real, they will fall in this region. And this parabola is separating the complex roots to real roots. And if you want a stable system, your coefficients are such that the B1 and B2 must be inside. If you plot a point B1 and B2, they should fall inside. Then it's a stable system. And this boundary equation, straight line equation, is given by that, and this boundary equation is given by that. I think the next slide shows you how to prove that. So stability triangle is important. If you have got roots, that is P1 and P2, you use the circle and find out where they are. If you have the coefficients, then you look at the stability triangle. Yes, that's okay. We've already said that. If you go to the next slide, stability triangle equation can be obtained by knowing the poles have to be between 1 and minus 1, and then taking one at a time. You just simplify this equation. You will show one straight line, the other straight line of the triangle. And that equation is given here and here. That's all. You need to know how to prove these boundary lines, okay? If you're asked to give a stability triangle, show the equation of the triangle, you should show this property from this. That's a basic simple example how to do this. And if you, that's basic algebra. If you've got any problems, you can ask us in the tutorial class. The same thing, what I've already explained, is just going back to explain, and I think the triangle is missing here, the triangle should be here, there, and the region, what I've already explained is already there, and the points about the parabola correspond to complex conjugate poles. It's all known. Next chapter, we are going to look at marginally stable. This is for stability. Real poles, complex poles. Now, one question you could be asked, if you have got complex poles, what does that mean? That means you're going to have a resonance system. If you've got a real poles, what does that mean? Oh, it depends. If you won't have a resonance system, you could have a low-pass filter like that, or you could have a high-pass filter like that as well. So normally, you should look at this way. Sometimes students have difficulties looking at it. Look at 0 here, there. Have a look at this one, right? Say I have got two poles here, two of them. So I write down 2 here. So I have got, think it this way. People don't normally. If I draw the frequency response of this, I'm only drawing one side, theta, h theta. I might get a kind of a low pass filter like that, a second order low pass filter. Now I say, right, I'm going to move these fellows this way. So I'm going to move this fellow this way at that angle and put it there, and this fellow there at that angle. They have to be same angle. This one and this one same angle. So if you start to do, let's fix the angle something like somewhere there, right? So as you move this up there and that way, this fellow will start and a little bit of bump like that, because it's not really these points are fixed, right? But it doesn't move further. So when as soon as you move it, it will give you this, and then you start to move this one in here, outside a bit, just a bit outside on the R. So what will happen is this will go pick up like that. If you say now you move this one inside here, what will happen? R is very small. In that case, it will come up there and with a small bump like that, or somewhere here like that, or it could be like that as well. As soon as you move outside, it will go bump up. But so if you want me to draw a bit more detail, this is what you get: a low pass filter like that with a real pole, and you just fix the resonance frequency. There it goes, has a little bump, then little more, and a bit more, and then sharper, and then very sharp. So this is R equal to 0.9. You're moving, and this could be complex. R is equal to 0.2. Same theta. I'm speaking theta fixed. And theta is fixed. I'm just moving this out, immediately become complex, then I'm going to move inside or move outside, depends on which way you move. Both of them have to move simultaneously, and you get that curve. That's the resonance curve. Next chapter tells you oscillator. What does that mean? That means I am going to move these poles there. They're going to be on the unit circle. They are resonant poles, they are on the unit circle. If you have it here, on the real circle, there's no good here. There's not much use to you. It's still stable, but it's no use to you. What is the end of the filter? But here, if you have got a resonance, but on the unit circle, then it becomes an oscillator. That's the next chapter. Digital oscillator. What is the oscillator? Well, in the lab, when you go and you've got a signal generator, an analog signal generator, you've got a couple of knobs there, you just fiddle around, you get sine waveform coming out. Or it could be a cosine waveform coming out, or sine waveform with a different amplitude, or sine waveform with a different frequency coming out. These are all analog oscillator designed using operational amplifiers, capacitors, inductors, and resistors combined, or only RC or LC, LR, or LC or RC. Okay, you can have all these oscillators. They are well designed oscillators, but you want digital oscillator. In modulation, like in telecommunication, you would have learned if you want to modulate something, you need oscillator. You need a carrier frequency. If it's analog modulation, you use an analog oscillator. If you want a digital modulation, you need a digital oscillator. So you should generate digital oscillator. Either you build in a hardware or use a special purpose signal processing processor to generate that. So what you're going to learn is how do you design an oscillator. Now, what is an oscillator? How do you design it? Important. Very, very important. Not many books cover that. You really need to know. So, digital oscillator can be made using a second order system with the appropriate coefficients. Never mind. Simple solution. What is a digital oscillator? You have a resonant pole on the unit circle. I'm going to show that to you now. So my question is, oscillator, I want my oscillator to produce this output. That's what I want. A is my amplitude, theta is my frequency of oscillation, and these are the sample number. I want to get oscillator coming out like that. How do I design it? Okay, let me take the step transform of that. Look at the transform table. It says Pz equal to that. You got that step transform? We now go and find out the inverse transform of that. So, we go there and say, right, Pz equal to Yz over Xz. If you take an oscillator, this is an oscillator, there's an output there. And there's an input as well, but in a minute, I'll explain. This is what, so you get your equation. The inverse multiply, take inverse Fourier transform. Inverse Fourier transform, you get output equal to that, input. That's your oscillator. Now, the question is this, you can ask, when you have a signal generator, when you have an amplifier, take an amplifier. If you got an amplifier, and you have an input and an output. You give an input signal, it's amplified, comes output. But when you have an oscillator, there's no input as such. You just turn on the system, it oscillates, it gives you an output, a sine wave. Amplifier depends on input. No input, no output. Oscillator, it doesn't depend on the input. It depends, just set up the system so that it oscillates. So you could say, for oscillator, to start, you need something. So as soon as you switch on the system in the lab, that's the start. It's an impulse you give them. So then it will start oscillate. So there's no input, special input. A DC itself is an input. When you turn on the switch, that's enough. There's an impulse traveling on the line, which causes the oscillation. For example, without giving one start, you can't start. For example, consider a pendulum. A pendulum, here you go, can't oscillate unless you just give a push. When you go a push, it goes up and come down, back there, keep oscillating. Right? So pendulum, you need to give a push to oscillate. Okay? Similarly, in this case, you need to give a push. Leave out for the moment. But is it right to say now, an oscillator, as I explained here, an oscillator only provides an output, there's no input. That means I could say input term should vanish for an oscillator equation. There shouldn't be any input term as such. But you must have an initial condition, definitely, to start a system. But there's no special input term. So I can say these two are 0 for an input term and oscillator. That leaves me, this is my oscillator, which if I rewrite them, that's my equation of my oscillator. Where theta is my oscillation frequency. Where Yn is the current output, Yn minus 1 my previous output, that's also previous output. By implementing that equation on the computer, you can let it oscillate. As long as you give an initial condition. No initial condition, it won't oscillate. It will sit there if you don't give initial condition. Think it. If this is 0 and this is 0, back conditions are, then if you Yn, what's going to happen? The whole thing is 0. So it will never oscillate. So you must have initial value here somehow, some particular value. If you have it, then it will start oscillate. Okay? So this is the equation. How do we implement this? Yes, next line. So once you have this equation, we write the equation, we implement the equation. Your lecture notes has it right. Now it's only wrong here. Well, it's just basically how we draw. So this is an oscillator, right? There's no input here. Here's an input, Xn, right? And no input, so that. So where's the output there? Divided by one sample, Yn minus 1, multiply that. Yn minus 2, multiply that. That's my oscillator. That's an output. In order to oscillate it to work, either I must have a value here or here. I must have a start value. If I don't have any value, if I put a 0 here, what happens? This will be 0, this will be 0, whole thing is 0, you will get nothing coming out. No good. You must have initial value here or here. It's like a pendulum. You must push it, or you bring the pendulum at that point and drop it, and then it's oscillates. So that's the initial value, or initial value is the push. So you could say, in order to get this oscillator oscillating, I could say simply, oh, I want to get this oscillating. So what I'll do is, I could just give a delta n here. Just the one value and then just all 0. That's enough to get this moving. That's exactly the same as pushing that. So I could give 1 here, delta n, it will oscillate. Or I could turn around and say, no, I don't want to give 1 there. I will select 2 values here at the start, which I have to work it out in a minute. Once I put that in, it will also oscillate. So 2 conditions, similar to this pendulum. Push, that's the delta here, or put there and drop it. That's the initial condition of that distance, or whatever the way you work it out. Okay? So initial condition has to be here, or you can set that to 0 if you want, but you must give an impulse. You must get that right. Okay. So how do you get the initial condition? So let's say this is my oscillator I want. So I say my y0 is a cos 0 naught, that's a. This is 1. Y minus 1 is that, is a cos theta. I know theta, I know what frequency I want to oscillate. So I can go back and then say, right, let me go back to my diagram. Sorry, come on. In this diagram, I could just say now, right, in this one, y naught, there, I'm going to put a, and here, I'm going to put a cos theta. If I put those 2 values at the start, a could be what? Then all I need is cos of the oscillation frequency you need. So if I put that in here, this system will oscillate. So that's what that is. And also, you can find out the oscillation frequency by using this formula which I derived in the previous slides, where V2 is 1 for us. For oscillator, V2 is 1. Why is it 7 triangle? Oscillator means what? It's on that line. That is V2 that's equal to 1. It's going to be on that line. So V2 is 1, which gives an oscillation. So from here, cos theta equal to minus V1. That's your resonance frequency of the filter. Here is a digital sinusoidal oscillator, and right, this example is a digital sinusoidal oscillator, and it's given here, and the input, and this is minus V2, and this is your output that you want. You've been asked to find out the value of V1 and V2 for oscillation. That's very easy. You write the transfer function first for this, which will be equal to 1 over 1 plus V1 set to the minus 1 plus V2 set to the minus 2. You write the transfer function first, and then you go on to the next one, where you write that, and then you say, okay, for oscillation, my 2 poles have to be on the unit circle. That's theta naught. That's R. So I write down that, and I know R equal to 1. I don't need to do it now. And expand this one, and you got this, and you take those 2, map them. You will find out same as I did before. V1 equal to that. V2 is equal to this. So that's what I've written. And for oscillation, R equal to 1. So V2 equal to 1, because they have to be on the unit circle. And then V1 becomes this one. So that's the condition for oscillation. So if you are given a structure, you are asked to find the condition for oscillation, that's how you do. Here is the second part. It says that your input is this given, and the output initial conditions are 0. If that's the case, as soon as you give this input, the system oscillates, continuously oscillates, it's self-sustaining. You have to show. How do you do that? You go back to your equation. This is our equation for an oscillator, and I have an input now. Input is given by that. It's given. Now you start n equal to 0. Okay? If you got n equal to 0, then y0 here equal to 2 cos 0 y minus 1 minus y minus 2 plus this. Delta 0 is 1. This is 0. This is 0 given already. So you get a sine theta naught. Now you put n equal to 1. You repeat it again. Keep going. From now onwards, this term disappears because the delta function is only 1 at n equals 0. This one will be 0, but this is not 0 because I have calculated. You substitute that in here, you get a sine theta naught, 2 cos theta naught. When you multiply, a sine 2 theta naught. You can see the pattern. It starts from a sine theta naught, now it comes a sine 2 theta naught, then it will go a sine 3 theta naught. It will come. So, that's what you have to show. You go on to the next one. You can now do n equal to 2. That. This is gone. This is you already know. This is you already know from the previous value. Substitute them, simplify them. You can show that equal to sine 3 theta naught. So you can see when you have 2, you got 3 here. So eventually you're going to have yn is equal to a sine n plus 1, because every time you've got 2 here, you've got a 3. If you've got a 1, you've got a 0. So it's got a, if they've got a 1, it could be 2 here. So a sine theta naught. That's what you have to prove, and that's what you're done. So, and so on. You just write down that. The next part is by setting the input to 0 under certain condition, you can still make the oscillation, find the initial condition. So you write the equation, input is gone, 0. Now you have to find that and that initial values. That means, for example, y0 and y minus 1. 2 previous, current and previous. Or 1 and 0. Or 2 and 1. Doesn't matter. 2 initial values. Better to do 2 initial values. I mean, 0 has the value and the value before, right? Because if that is 0, this is minus 1. If this is 1, it will be 0, this is minus 1. You can have anything, as long as there are 2 consecutive values. Okay. So I set that to 0, and I put n equal to 0, and this is what I get. If for oscillation, I want to make sure I don't want any cosine term, I could make that to 0. That's one condition I'm going to get. So if I do that, I have got that part. Now I go and say y1, y0 here. When I say y0, I get minus y minus 2. That's what I have. And what is y minus 2? You'll know. Well, y minus 2 is this. You go back into your equation. What is y minus 2? Yn is equal to a sine n plus 1 theta. That's what you have. So what is y minus 1 is? Y minus 1 is equal to a sine y minus y minus 2 I want. Y minus 2 is equal to a sine minus 2 plus 1. That will work out to be minus a sine theta naught. That's my initial condition for y minus 2. So I know for y minus 2, that's my initial condition. I want for y1 is that. If I do those two, I'll get the oscillator oscillating. Have a relook at it again and see whether you understand. If you follow, sorry about the scribble, I was just scribbling too fast. So just to make sure that's gone, okay? Then you substitute n equals 0, you get this equation. You get rid of that, you can do that automatically. You don't need to say no cosine terms, just get rid of that. So set that to 0 and that. Then you have to find out y minus 2. You go back to your original equation. What is y minus 2? Y minus 2 is a sine theta, that's not right, a sine theta naught. Just now I showed you, you go yn equal to a sine n plus 1 theta. You substitute n equal to minus 2, you get that one. And they are the initial conditions. So with those two initial conditions, without any input, oscillator will oscillate. Here is another type of oscillator which produces sine and cosine. The first oscillator will produce sine waveform or cosine waveform. But in modulation scheme, you will find you need sine, cosine at the same time. You cannot have two separate oscillators because this may start early, this may start late. The phase difference will cause problem in detecting the data later on, digital data. So we want to make sure one oscillator produces two outputs. They are both synchronized. You get one oscillator producing two outputs, both synchronized, it will use oscillation. So we need an oscillator both producing the same output, but same time, sine and cosine. That only can be done. You generate two oscillators, but they are coupled, so that this cannot oscillate without this, and this cannot oscillate without that. So I've got a two first order system, one here, one here. I couple them like this. When I do that, this cannot oscillate without this, and this cannot oscillate without that. Therefore, both will start at the same phase. One gives sine, one gives cosine. So how did I derive on this particular equation? How do I know this is what gives simultaneously the cosine and sine waveform? Well, we have to derive the equation to show this is possible. So we go to the next slide, where we start with a trigonometric equation, where cosine, what we want, cos A plus B is equal to cos A cos B minus sine A sine B. You've done that? That's the trigonometric equation I'm using. Now I'm going to say yn is cosine theta, that's what I want. And xn is sine theta, that's what I want. Two outputs. So I go and substitute here. Let yn plus 1. How do you get yn plus 1? Replace n by n plus 1. Yn plus 1 will become cos, in this equation I substitute here. Look here. I said this will be yn plus 1 is cos n plus 1. So cos n plus 1 is yn plus 1. Cos theta is still there. Cos n theta is yn. I have it. Minus sine theta will be here. Sine n theta is xn. So that's one equation. Okay? You with me there? Basically, all I'm doing is I'm substituting these ones in this equation. I get that. Now I replace, wherever n, I'm replacing by n minus 1. If I do that, this will become yn. This becomes cos theta yn minus 1. This becomes sine theta and xn minus 1. That's my equation A. Now similarly, I start another trigonometric equation, which is sine A plus B. Sine A plus B is sine A cos B plus cos A sine B. Correct? And that's the equation. I've done it. And similarly, go back here, substitute these ones in this equation. This becomes xn plus 1, then yn, xn minus from here. Now you replace n is n minus 1, that will become n. This will become n minus 1, this will become n minus 1. So I've got another equation. I call that B. I'm going to implement that one and that one together. Then I get xn is the sine output, that's the cos output. Okay? Let's go to the next line. So I write those equations in a particular matrix form, but it's not required. Matrix is not required. I just wrote it as in this form. Yc, Ysn. This is the equation that you had in the first two equations, A and B. I just combined them in this form. Sorry, there's one thing missing. Just give me a second. So I just go back, and then if you implement that structure B and A, just implement them as we did before, you get this structure. So I've given the structure and I've derived the equation, and from the equation you implement this one. Okay? I just want to do one example for you. In this example, you have been given an oscillator as a coupled equation is given. Draw the structure for this realization. Initial conditions are given for you, and then you have to show, you write the difference equation. Right. Okay? So these are the coupled equation. From the equation, like I just wrote the equation, and I can draw the structure, which is exactly same as what you had. Basically, you can start with the yn, and you say cos theta naught yn minus 1 you need. So you've got yc minus 1 multiplied by cos theta, you get that. Then you get sin theta naught multiplied by sine. So you get a sine output, sine and minus 1 output, and multiplied by minus sine theta means you get that output. Similarly, the other one. Okay. Now you have to show it is oscillating and providing sine and cosine. How do you do that? You start n equal to 0. Do the sine part first, it's 0. And n equal to 0, do the cos equation. The two equations I have above, you substitute them. Then n equal to 1, you put, because a cos theta naught. N equal to 1, you find a sin theta naught. So it is correct. Then n equal to 2, you work out, you get cos 2 theta naught. N equal to n, if you continue this, it will end up as, you can see, cos theta naught started with 0, it started with cos theta naught, cos 2 theta naught, so it will end up with cos n theta naught. Similarly, you can show it with cos n theta, sin n theta naught. So that structure, by iterating like this, few examples, few values, you can say it is sine and cosine. Here's another example of a question where you have been given the transfer function of an oscillator. There you go. You've been given this, and you've been asked to find the impulse response. So you have to show the impulse response to this. So what you do, you go back from the set transform, write down set transform of sine waveform, which is this, right? And your inverse of that, if you work on the inverse of this one, which implies the inverse will be sin n theta naught un over sin theta naught. That's your inverse. And that gives you, that is coming from here. So you can show this is equal to that. Therefore, the inverse is Hn. The Hn will be equal to this one. You just manipulate the table. So basically, if you're not sure, this is the way to do it. You're not sure about it. You just go back and find out. You've been asked. You've been given this. This is equal to that over. You write this one, and this is what you have to show. So you start with the transform of this, that gives you this. Now what you do, you move this fellow, that one, out underneath. You can still do that without disturbing. If you do that, you get that over that. That's this one. And that gives you that over this. That over this. Which is our head stat. So we are saying, if you take the set transform of that, you will get this. Therefore, if you take the inverse of that, that's what your impulse response. Okay? Now, frequency of oscillation should be this. You have to show change in frequency of oscillation. This is slightly different from what you've done. And what you need to do, you start with the frequency. We know this is the oscillation, theta naught. So you take beta 1 and differentiate. Change in beta 1. V1 is delta V1 is minus 2 sine theta naught, delta theta naught. It's like dV1 over d theta naught. That's what you're finding out. And we know that delta theta naught, what is theta naught? Theta naught is 2 pi Fa over Fs. So you can say delta theta naught, if you want, is equal to 2 pi delta F naught over Fs. So that's what I've done here. And if you substitute that, right, and your resonance, and then you just cross multiply, you get delta F naught become this. This is your resolution of your frequency resolution. So how much you can change the frequency from the resonance frequency, how much you can change, it depends on your resonance frequency and the coefficient. Also in sampling, the sampling is a constant. So you can by changing the coefficient, so the coefficient at a certain bit of accuracy that is required in order to get a fine resolution. This is just an example for you. So we come to the last section now, which is the notch filter. Notch filter you've already done. You know how to do a frequency response, but I still want to run through the notch filter. Now, when a zero is placed on a set plane, the frequency response will be zero based on the unit circle on the set plane. Will be zero. The corresponding point now is placed at a given point on the, not on the set plane, on the unit circle. Unit circle. A pole, on the other hand, produces a peak at the corresponding frequency point. So we know that. We've done that before. If you've got a pole, it will be a peak. If you've got a zero on the unit circle, always come like that. Yeah, it touches. If it's not on the unit circle, it will come around like that. If it's on the unit circle. So poles that are close to the unit circle give rise to a large peak, whereas the zeros close to the unit circle produce a trough or minimum. That's strategically placing the poles in zero on the set plane, we can obtain a particular frequency response we need, such as selective filters, very selective filters. So basically, you're going to say, right, here's my poles. I could have a pole there, two poles, and also I could have a zero somewhere closer to here. Here, I could get a select. They can't be there. It should be here, symmetrical. I could get a particular filter. So let's go on to look at that. There is an example here. I demonstrate this through using an example. We want to do pole zero placement method to derive a transfer function which gives a digital notch filter. Notching means removing a frequency. Like 50 hertz hum, mains hum you want to remove, you need to pass the signal through a notch filter. Notching means it just takes out that energy, that particular frequency. So in this case, here is the filter. And this hertz, that should be taken out. But the filter should be flat like that, take out that frequency, and then goes back. So all these frequencies are passed, these are all passed, that's taken out. That's called a notch filter. How do you do that? Notch frequency is given 50 hertz. The bandwidth, this bandwidth here is given 10 hertz. Sampling frequency is 500 hertz given. And the radius, the area from the poles is given by this equation. It's given to you. You can prove that as well. Maybe we should prove that later. So what do you do? First find out what frequency you want to reject at. We want to reject at 50 hertz. So sampling is 500. 50 divided by, so 2 pi times 50 over 500. That's how we find out our frequency, which is 0.2 pi, plus or minus 0.2 pi. Work out 36 degrees wherever, and 0.2 pi is, that's where we have to place the complex zeros. Now, to achieve a sharp notch filter, you really have a sharp notch filter, and on the either side of the notch frequency, we need to have a complex conjugate zero space at the radius less than 1. You can have it, you could, yeah, we conjugate poles, not zeros. There's mistakes. Sorry, there are one or two. There's no mistake on the lecture notes, but just when we typed on the PowerPoint. Okay, now where is the R? We have been given the formula, bandwidth 10 hertz, plus or minus 5. Fs given 0.937. So you go into the unit circle and work out the distance. This pole must be placed at 0.936. On that line, you put zeros there because notch the frequency. So what does that do? If you do that, what are you going to say? You're going to say, right, the poles will produce me something like that and down. But it's 0.97, so it won't be very sharp like that. Zero at the same frequency, so it will go down there, dip like that, and then go like that. So what will happen? This will dip it down, this will pull it out, So when eventually this has to be 0 at that point, you can't go further. So the whole effect will be a kind of a step, and then it's a bandwidth, and it just flattens out. That one cancels with that 2-second order. This will be same. So if you look at the overall response, you can write the transfer function. The transfer function for this, you write that one first, then you write that one, and if you do that, you get zeros at that point, and there's no r equal to 1, and that's the pole, and if you multiply them out, that is your transfer function. You can see the transfer function, and the frequency response is going to be, this is the frequency response, you can see. So what you have designed is something like that, and you design something really steep like that, and the overall response is the red one, which like that and like that. So the transfer function is given, and this is how you design a notch filter. Right, Chapter 3, CD1, CD2, this is the last CD, and I just want to give you a summary of all the thing I have done in Chapter 3, right? If you have gone through the CD, and if you're going through the tutorials as well, at the end of the chapter, you need to know the following things, at least. So, you need to know block diagram conversion from an analog to digital, and back to digital to analog. That's A to D converter, D to A converter, you should know, and you should know what's quantization error, you should know aliasing, you should know how to calculate signal to quantization noise ratio. All of those should be done there. Well, which I have mentioned here, quantization error, and how do you reduce the quantization error, all you should know. And also you should be able to calculate the signal to quantization error ratio for a simple sine waveform would be fine. Then you need to look at sampling of analog signal, in particular deriving mathematical relationship between the analog spectrum and the digital spectrum, and to show that the digital spectrum repeats of the analog spectrum within the half the sampling frequency. And you should be able to derive that equation and show that it's a repetition. And not only that, the repetition, if the analog has an amplitude of A, on the digital spectrum it will be reduced by A divided by T, the sampling frequency T. And a lot of people miss out normally, and you must look for that. Then the sampling theorem and the Nyquist frequency. I've done lots of examples, and you should know what is sampling theorem, what's the Nyquist frequency. You should know that without any difficulty. If you don't know, go back to the lecture notes. Then you should draw a spectral diagram to show how the aliasing happens, and sketch magnitude spectrum plot, and to demonstrate the aliasing. And using the spectral plot, you should be able to show how you avoid aliasing. And then you need to understand digital to analog conversion, and you should show your understanding using the mathematical and stochastic explanation. I've given both. Mathematical is using a sinc function, how do you interpolate, and or you just throw some waveform and to show how do you do that. And one of the important things on D to A conversion that you have to understand is that when you send the signal out, you've got a rectangular pulse comes out of the D to A converter that produces the sinc function that uses as the interpolation function. Also, you should know in the D to A converter, the low pass filter that you use is exactly same as the anti-aliasing filter. Okay? Calculation of alias frequency using this formula, using k various values between +1, -1, +2, -2, any values, and you should know how to use the formula. Especially, you have got a spectral component available outside the sampling frequency, half the sampling or sampling frequency, and if you do sampling lower than the spectral content outside the sampling frequency, then you know that will be reflected back into the fundamental region. We have done a couple of examples, and you should relook at the example and say where this is happening. And all those examples you should know. Then we looked at the type of digital filters, SIR and IIR filters, and the different properties of them, and the impulse response of them, and also the coefficients and all of those, you should know the difference. Then conversion from FIR and IIR difference equations to transfer function and back again. So from the transfer function, difference equation, transfer function. You've done that many times. You look at non-recursive filters and understanding phase delay, group delay, and definition of linear phase filters and when to use a linear phase filter. You don't need to design them. Design will come up later on, but you need to know. Then you look at the recursive filters, which are all pole and pole zero filters, and then you look at the cascade, parallel, and canonic structures, and why you need canonic structures. If you are given a transfer function, a simple transfer function, and how to calculate a 3 dB cutoff frequency, if it's a low-pass filter or band-pass filter, you need to know that. You should be able to plot the magnitude response and the frequency response of a simple first-order or second-order IIR filter. Normally, first-order we can do it, and we can cascade many first-orders to get second-order, or two first-order gives you second-order. You are able to distinguish between a low-pass and a high-pass filter based on the difference equation, based on the transfer function for both FIR and IIR. So, for example, you've got Hstat is equal to 1 plus Z minus 1. You get Hstat is equal to 1 minus Z minus 1. You get Hstat is equal to 1 over 1 minus Z minus 1. And then Hstat is equal to 1 over 1 plus Z minus 1. You should be able to know the difference between all those four basic filters and which is the low pass, which is the high pass. This is the two FIR filters, it's a low pass and a high pass filters, and similarly you have got IIR filters. Okay? Given an FIR filter, you should be able to draw the magnitude and a phase response. We have looked at that, and then explain the relationship between magnitude and phase responses. And you know when the magnitude response goes to 0, there's a phase change on the phase response. You have done that, and you should be able to do that. Then you should know the difference between the minimum, maximum, and mixed phase filters. You should be able to demonstrate examples. And then you should look at their magnitude responses when the filter zeros are reflected about the unit circle. Then you look at all-pass filters and how do you design all-pass filters, basic all-pass filters, first-order all-pass filters, and show their magnitude response constant, but their phase response is non-zero. Be able to derive transfer function for a second-order resonator filter, and should be able to analyze the stability of the filter in terms of pole zero, in terms of stability triangle. And the stability triangle, you should be able to derive the equation for the boundary of the triangle using the method I have shown you in the lecture notes. Then you look at principle of stability, marginally stable and unstable filters, and equation of digital oscillators. How do you derive equation of a digital oscillator, and how initial conditions to be set up in order to get the oscillation running. Well, that's the end of this chapter. And during this chapter, in some slides I've probably ran very fast. Sorry about it. If you don't understand, you can ask us in the tutorial class or to come to my discussion class. So this chapter is the real fundamental for digital signal processing. You must have a full understanding of this chapter before we move on to the next chapter. Okay? Thank you. If you have any problem, any feedback, just please feel free to contact me. Okay.